assignment on the whole, show of hands, who feels like we're going to do a scale of 1 to 5. Sorry, yeah?
I struggle with the span.
Span?
Yeah, same, I was about to say that.
Okay. Span is weird. Like, it is weird. Roughly, span is just so let's say that we want to like reach any point on this whiteboard, right? And this is like maybe the origin or something, and I want to be able to draw any arrow to reach any point on this whiteboard. If I have like 2 vectors like this, then all I need is the 2, and I can reach any point on this board using like some scalar of this. So maybe like if I wanted to get here, I could use like negative something of this, and then maybe I can't draw this right, but like negative something of that vector, right? So like I'm using like a scalar combination of the 2 to get to any point on the board. So in a sense, using these 2 vectors, if this is like V and this is U, then the span of V and U is like the whole board, right? There's a formula for it, which is the span of, what is it, alpha 1 U1 plus alpha 2 U2 plus alpha n UN, such that alpha I is in your field, not real, sorry, it's in your field. Well, I shouldn't say that, that was kind of wrong. Span of those vectors, U1 through UN, is equal to that. So it's like some scalar times U1 plus some scalar times U2. So it's like every possible linear combination, everywhere you can reach using those 2 vectors. It's like every vector you can make by using some linear combination of the vectors that you get. It's like everywhere you can reach. Yeah, that's pretty much all span is, yeah.
What are the values of any of the
Of like the U's?
Of like the A.
The A's. You sort of don't need to. You kind of don't need to, unless you're like trying to find a particular vector. So like if I wanted to find this particular vector, right? You would need to find like how much you stretch this by. This would be like your alpha 1 maybe, and then how much you stretch this by, and that would be your alpha 2, right? From the original vectors. So you could find it. I don't think you'll ever need to. I don't think you really generally do need to.
Any vector span?
Sorry?
Can any vector span the space?
Not necessarily, right? So if I took like this vector here, and I took this vector here, those are 2 vectors. But their span, if this is U and this is V, their span is like the whole line, right? It doesn't, like, there's no way I can use those 2 vectors to get over here, right? It's never going to happen, right? So that's sort of the idea with span. Yeah?
How do you set span?
How do you prove a set spans a vector space? So like as an example, if you picked the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, then if you span, or if you do like alpha 1 times this vector, plus alpha 2 times this vector, plus alpha 3 times the other last vector, right? What you do is you write it out like this first, and then you try and simplify it, right? So you get, if you combine these together, you get like alpha 1, this one would be alpha 1, 0, 0. This would be 0, alpha 2, 0, and 0, 0, alpha 3. If you add those together, you get alpha 1, alpha 2, alpha 3, where those alphas can be any number, right? So when you see something like this, where any of those alphas could be any different numbers, you can make up any vector in R3, right? So the set of this, such that the alphas are in your field, is equal to F3, the whole vector space. If F is R, then it's R3. Does that make sense? Yeah.
Express it as a linear.
Yes. and then try and combine it into one thing and see what does that thing look like, right? Like if I had like, for example, if I had like this, right? That wouldn't span. Like you would end up getting like, what would you get? Like alpha 1 plus alpha 3 and alpha 2 plus alpha 3. And then 0 down here. If you add all of them together, so you get 1 alpha 1, 0 alpha 2 is 1 alpha 3, so on. But not every vector in F3 in this case has a 0 in the last element. So that doesn't span the whole set, right? You need to make it like generic, right? If you can make it like pick values of alpha 1, alpha 2, and alpha 3, and it can make any possible vector, then it spans the whole space. That's sort of what we have here, right? This plus this equals this, right? So then in that case, well, in this specific case, you're left with the 0 at the bottom, right? So it's just about like taking what you have and expanding it. No problem. Okay, let's move on and talk about this week's stuff. How far did you guys get in, was it yesterday's lecture? Did you start like lecture, like the next set of notes? Okay.
I skipped lecture. But he didn't like it.
Okay, yeah, seems about right. He's gonna run out of material pretty soon. He skipped a few already. Like I think he skipped 3 now.
Oh, he skipped
Yeah.
3?
Yeah.
Like,
Oh, did he? Nice. Okay. So, yeah. So how far did you get out of curiosity? Because he hasn't posted the notes for me. You didn't get to rank? Good. Did you do nullity? You did nullity? Okay. And you did image, but you didn't do rank. Cool. Range is image. Same thing. Okay. So, all right. So let's start with the idea of linearity. So if you have like a transform, which is just a transform, anytime you hear that, that's just a funny word for function. It's the same thing. Okay? It is a function. That is all it is. There's no difference between a transform and a function. As far as I'm aware, I don't think there is. So for you, just, it's a function. It goes from, in this case, a transform goes from one vector space to another. Maybe that's the difference, is that it's a function from one vector space to another. I don't know, who cares? It's a function. A transform is linear if it has to meet 2 criteria. The first one is additive. So if you take any 2 vectors from V and you add them, you can like pull them out of the transpose, or not the transpose, the transform. Like that, right? And the second thing is homogeneous, which is that you can pull out a constant, right? Cool. So if anything, and this is a general thing in math, if anything is additive and homogeneous, we call it linear. And this is why we call it linear algebra. Maybe a lot of people, like in my earlier linear algebra classes, like 2050, they often say like, why is it called linear algebra? Because sometimes it doesn't feel very linear, you know? It's because of this. That's it. And maybe you're thinking like, what does transformations have to do with like matrices, right? Other than you can transform matrices, right? But matrices and transformations are actually the same thing. I hope that kind of scares you a little bit, makes you feel a little uneasy, because it should. Let's go through an example of that. So let's say that I have a transformation that maps from, well, we'll say it maps from R2 to R2. As an aside, what do we call a transformation that goes from a set to itself? Yeah.
Operator.
An operator. Yeah, it's an operator. So let's say I have to find a transformation such that T reflects a vector V over the line y equals x. So like as an example, if I have like this vector here, right? This is my line y equals x, it like reflects it over that line. It's a linear transformation. I'll let you prove that, but if you want to. But the question is, how do we write this as a matrix? What you do is you take your basis and you apply T to each basis element. So in this case, our two basis elements are 1, 0 and 0, 1, right? So then we think, okay, well, if T reflects whatever you put into it over that line, then what happens to 1, 0, which is like I hat or E1? What happens to that unit vector? Yeah, right? It gets like sort of, maybe I should draw it. It gets like, if it's getting flipped over this axis, it's going to like end up over there straight up, right? So it becomes 0, 1. And then what happens to 0, 1? Yep. 1, 0, right? Cool. So that's what we have. And basically you're done. If you want to put a transformation into a matrix, you've kind of just done it. This should be T of E1. This should be T of E2, and however many basis vectors you have, you just keep adding them. And so T of E1 is this, so it's 0, 1. T of E2 is this, so it's 1, 0. So that matrix represents this transformation. We just turned words that are kind of confusing into a matrix, which is easy, right? We know how to do matrix multiplication. So now for any vector, if I wanted to multiply this by like, let's say that I wanted to figure out what happens to like -5 and pi, right? That would be hard to try and figure out, like, you know, like just logicking it out. But like, you can do this matrix multiplication, right? It's not too bad. And then you get your answer. And that's it. So any transformation, any linear transformation at all can be represented by a matrix. What would it mean if I had a matrix that was like this? What kind of transformation would that represent? Well, remember the columns represent what happens when you apply the transform to each of the vectors, right? So because this is like 3 by 2, it maps from a 2-dimensional vector space to a 3-dimensional vector space. I don't know if you can see that, but like here we have 2 dimensions and here we have 3. So we're going from 2 dimensions to 3. Does that make sense? Cool. All right. So a bit more notation. Don't have much whiteboard space, so apologies again. The linear transformation. So if I write like this, do you know what that means? That notation? Yeah.
I'm kind of just taking a guess because of how it was used.
Yeah. I don't think you defined it.
Set of all linear transformations from W.
Yep. Such that T is linear. exactly. So hopefully that makes some sense. All right. Okay, so say that I have some transformation in that set, V to W. So it's a linear transformation from V to W. Then I say the kernel of T, this is kernel, and I think there's another word for it, null space. Is that what they call it? Yeah. Kernel is what you'll see in the real world. The kernel of T is the set of all things, set of all vectors such that T of V equals 0, where V is in that big V. So it's the set of all things that get mapped to 0 in your vector space. I think a really good example of this is that consider the linear operator D, which is the derivative, right? The linear operator D, it'll take in a, let's say it takes, well, it is linear. You should kind of maybe vaguely remember that from calculus. Say it goes from like, say this one I'm considering, it goes from polynomials of degree 3 to polynomials of degree 2, right? Because if you take the derivative, it's always going to go like down a degree, right? So P is a linear transformation from P3 to P2. What would be the kernel of D? So what's the set of all things that when you take the derivative of it, it equals 0? Yeah, constants. Yeah, right. Did we do this in the lecture?
Yeah.
Okay, good. That's a good example, right? Yeah, so the kernel is a set. And what's interesting is that it forms a sub, or I guess maybe I should probably properly write this as like P0, set of all 0 degree polynomials. That always forms a subspace of, in this case, P3, the first thing that you have, right? Like the domain. Does that make sense? Cool. So then another definition is that the dimension of the kernel of any operator, we define that to be the nullity of T. So yeah, that's, if you hear the word nullity, it just means the dimension of that kernel, right? Because the kernel is a subspace, so it's a vector space. It has a dimension, right? In this case, what's the nullity of D? Is it? Yep. Yep. Because a basis for the real numbers is like 1, right? Because if you do like alpha times 1, you can generate any real number. Yeah. So the nullity is 1, has 1 element. Okay. So then, what's the image of a transformation? Say that I have, let's say that I consider D, which is the derivative, going from P3 to P3, right? This is the domain. This is the codomain. So whenever you're asked like, what's the codomain and what's the domain, it's always what you see like in the function itself or in like the definition of the function, right? The image is kind of like, in reality, what is it actually gonna hit, right? What's it actually, like what are all the things that D could possibly reach, right? There's a few different notations, either like IM of D, or like range of D, or sometimes you'll just see like D of P3. Any of those are reasonable. So in this case, what's the image of D? Yeah, why? To one less, right? So like even if I say that this function goes from P3 to P3, in reality, it's not going to hit everything in P3, right? There's some polynomials in P3 that I just can't reach, right? So yeah, the image of D is P2. It's always like a, you know, sort of a smaller piece, not always, but. So we say that well, this applies to any function, and I think this is stuff you did in like discrete. We say that any function is surjective, which is another word for onto. You've heard of like onto functions. If the image of that transformation is equal to the codomain of that transformation. In this case, well, let's say that T goes from V to W, then it's equal to W. So in other words, if it reaches everything in the codomain, then it's surjective. Does that make sense? There's one more if, which is, does anyone know what it's called? One more like thing like that. Injective. What is an injection? What does it mean for a function to be injective? So, one-to-one. So that means if I do T of U, if T of U equals T of V, then that means that U equals V. That is, so is D injective? No? Why? Exactly, right? So like the derivative of x squared is the same thing as the derivative of x squared plus 1. They're both 2x. But that doesn't mean that x squared equals x squared plus 1. They're two different things, right? It means it's non-injective. Okay. I think that's everything I want to cover, since you didn't